There's a lot that's not very well understood about trace evaluations. Let's look at results, conjectures, and questions related to immanence and totally non-negative matrices. Now, regarding totally non-negative matrices, we're going to be working with symmetric group traces. The Stembridge in 91 and 92 prove that for all irreducible characters, chi lambda of the symmetric group, we have the chi lambda immanent of A is greater than or equal to 0 for all totally non-negative matrices A. And he conjectured that monomial traces satisfy the same. That is, if we look at the phi lambda immanent of a totally non-negative matrix, then that's going to be greater than or equal to 0. Now the conjecture is a stronger statement. Because since we have irreducible character chi lambda equals the sum of Koska numbers times monomial traces, this implies that the irreducible character immanent of A is the same sum of monomial characters, monomial trace immanence of A So if we knew that all of these things were non-negative, then a non-negative linear combination of them would imply that the irreducible character immanent evaluated at A is non-negative. So this raises a couple questions. First of all, for what traces theta is the theta immanent of A greater than or equal to 0 for all totally non-negative matrices A? And then for these traces theta, can we combinatorially interpret this immanent of A in terms of paths in a planar network G? So A is, since it's totally non-negative, it has to be the path matrix of some planar network G. And if we're applying some function to it, maybe that has some interpretation in terms of the paths in the planar network G. So let's make a chart of what's known. So make a column for traces and let's make a column for whether the immanent corresponding to that trace applied to A is greater than or equal to 0 for all totally non-negative matrices A. And then another column for a combinatorial interpretation. So if we look at irreducible characters, then by Stembridge's result, yes, this is the irreducible character immanents of totally non-negative matrices are non-negative. But he proved that without finding an interpretation in terms of path families in the planar network whose path matrix is A. Now, induced sign characters are characters, which means that they're non-negative linear combinations of irreducible characters. So if these immanents give us a non-negative number, then non-negative linear combinations of them will also. Now in this case, we know a combinatorial interpretation, and you did it for homework. This counts column strict path tableau of shape lambda transpose. And that comes from the Littlewood-Merritt-Watkins identities that say that this immanent is equal to a sum of products of minors. Each one of those products represents some path families that are going to go in one column, and they can't intersect each other. But when we put the paths in a tableau, paths in one column can intersect paths in another column, but there's just no intersection within one column. Then induced trivial characters. Well, induced trivial characters are characters, so they're non-negative linear combinations of irreducible characters. So the immanents are non-negative linear combinations of these immanents. So if these give us non-negative numbers, then those two also. And this was also in homework. We don't have a super nice interpretation, but it is something we can count. And these were row closed path tableau of shape lambda. So within any row, if we look at all the sources of paths in that row and the sinks of the paths in that row, then it's the same set, the same index set. The path family doesn't have to be of type identity. Just the set of sources in one row and the set of sinks in that row have to be the same. Alright, then we've got this power sum trace, which is not a character, but it has a very nice form. So it turns out, yes, that's totally non-negative. That is, yes, we get a non-negative number when we apply this immanent to a totally non-negative matrix. And that's because the power sum trace of W equals Z lambda if the cycle type of W equals lambda and 0 otherwise. So that means that if we take the chi lambda immanent of A, this is a sum of all permutations. We won't get any whose cycle type is different from lambda. And we're just putting this coefficient z lambda next to this permutation monomial. So for every permutation of cycle type lambda, we could think of, so this is paths from source 1 to sink W1, source 2 to sink W2, etc. And that path family, well, what ends at W2 we can think of as starting again at source. What ends at sink W1 we can think of as starting again at source W1 and then ending wherever that goes. So that if we look at the cycle type, then these paths are gonna, we could sort of wrap the planar network around a cylinder, and we get something going around lambda 1 times and then something else going around lambda 2 times. So we could say these are cylindrical tableau of shape lambda, and then z lambda is going to be, well, it's a positive integer, so we'll just have, well, a positive integer of a cardinality of a set. Let me put the monomial traces up here, and then we can do an example of the cylindrical tableau. So this is open. Stenberg has conjectured that if we take the monomial trace immanence of totally non-negative matrices, that we get a non-negative number, but that's not known to be true. So obviously the combinatorial interpretation is open. Actually, Stenberg proved this for the special case of lambda being a rectangular rectangular partition. So k to the r, that is, if we have k r times. And in that case there is a combinatorial interpretation. And I'll show you that too after we do an example of cylindrical tableau. So we know that the corresponding immanents are going to give us non-negative numbers if we apply them to totally non-negative matrices in all these cases except for monomial traces. I'm not including the forgotten traces here. And we have combinatorial interpretations for 3 of the 4 yeses, but we don't have a combinatorial interpretation for the irreducible character immanent evaluations. So let's pick the partition 2-1. Now we're going to need Z21, which is, now these Z's, remember, are a product of all of the entries, the components of the partition, times a product of multiplicities of parts factorial. Now, nothing here appears more than once, so we'd say times 1 factorial times 1 factorial. I won't write it. So that's just 2. So that means that this psi 2-1 immanent of A, if A is 3 by 3, is 2 times, we're just going to include the permutations that have cycle type 2, 1. A1, 2, A2, 1, A3, 3, plus A1, 3, A2, 2, A3, 1, plus A1, 1, A2, 3, A3, 2. So we can see just by looking at this formula that it's definitely going to give us a non-negative number if we apply it to a totally non-negative matrix, because it's non-negative number times the sum of non-negative numbers. Then, so the only question is, how can we interpret these? So this is all paths from source 1 to sink 2, all paths from source 2 to sink 1, all paths from source 1 to sink 3, etc. So let's look at a very simple planar network here. And its path matrix A, which is from 1 to 1 we have a path, 1 to 2, not 1 to 3, 2 to 1, 2, and 3, 3 to 1, 2, and 3. So what are we counting here? Paths from 1 to 2, 2 to 1, 3 to 3. So it's one path family there. Or several path families. I think it's only going to be one in this very simple network. So we have a path from 1 to 2. And then a path from 2 to 1. So we can sort of think of this path as coming back to 2. So it ends at 2. And then going to 1. So this cycle here is, well, the cycle notation of that permutation is 1 and 2 in a cycle and 3. So we can think of this as going from 1 to 2, looping around the back, and then 2 to 1. So we can think of that as, maybe I'll put the dotted lines around the back. So go from 1 to 2, sneak around the back, 2 to 1, sneak around the back, and end where you started. Actually, this should, if I'm drawing it on that planar network, let me put the planar network in here first. So go from 1 to 2, loop around the back, go from 2 to 1, loop around the back, come back to 1. So I'm saying cylindrical because when we go off the picture on that side, we end up on the picture on the left side, sort of in the same height. And then we have one path going from 3 to 3, and then you can think of it looping around the back and coming back to where it started from. So maybe a good way to write this would be in a tableau where we've got a path from 1 to 2, and then a path from 2 to 1. So in this row we've got the path looping around. Every path starts where the previous one ended, including the last path, which ends where the first one starts. Alright, so we can do that for, so I guess this one's going to be 0, because from 1 to 3 we don't have any paths. So in our example that one's 0. And then, so we could have a path from 1 to 1, and then another path from 2 to 3, and a path from 3 to 2. So the path from 1 to 1 is going to go like that. And then from 2 to 3, and 3 to 2. So again, we can think of this as wrapping around a cylinder. We go from 2 to 3, and then we end up on the left side at 3 again, and then we go down to 2 on the right, which ends up at the left side at 2 again. Alright, so that explains these two products. And then we need to explain the number 2. What's going on there with 2? Well, 2 is 2 times 1. So we're multiplying the lengths of these rows by each other. So there should be something we can do in 2 ways to this row, 1 way to that row. And what we can do in 2 ways to this row is start it at either position. If this row were k long, we'd be multiplying by k, and we could start it in any one of those k places. So we could say that this loop, which goes around twice, starts at 2 rather than starting at 1. And then the second part goes from 1 to 2. And here, oops, I wanted to start the second part. So we could start at 3 rather than 2. And then that one-to-one loop can only start in one place. So I guess in this example, we have the psi21 immanent of A equal to 4. A12, A21, A33 is 1 times 1 times 1. This is 0, we said. A11 times 2, 3 times 3, 2 is also 1. So we have 1 times 1 plus 1 inside the parentheses. 2 times 1 plus 1 is 4. Alright, now let's look at the special case of the monomial trace immanent that Stambridge proved evaluates non-negatively. Alright, so if lambda equals k to the r, that is a partition that has r parts equal to k, then that's a sum over all ordered set partitions I1 through IR of type, no, actually IK is easy to get confused because they're ordered set partitions of type k to the r, opposite of what this, no, r to the k, opposite of what that one is. So subset of size r, subset of size r, subset of size r, k of them. And then it's determinant of the I1, I2 submatrix times determinant of the I2, I3 submatrix, etc., up to determinant of the IK, I1 submatrix. So, for example, let's say lambda equals 3, 3, 3, 3. Then we're going to have a sum of a product of 3 4x4 minors. Each one of them is going to represent a non-intersecting path family, or many non-intersecting path families, from 4 sources to 4 sinks. So it's going to be something like, go from 4 sources to 4 sinks. and then it wraps around again, and we're going to go from from 4 more sources to 4 different sinks. And then we'll wrap around a 3rd time where those end and go back to, oops, this is supposed to go back to where that one started. So the second red path is supposed to end where the second blue path started. And then the 3rd red path is supposed to end where the 3rd blue path started. And then the 4th red path ends where the 4th blue path started. I was counting from top to bottom there. And since we have minors here, so these 4 paths don't intersect on their first time around, and then they don't intersect on their second time around. But what happens in the second time around has nothing to do with the first time. So we could think of this as a path tableau where we have 3 columns of size 4. And the paths on the first pass around look sort of like that. And then actually we started with blue, didn't we? So the first time around they look something like that. And then the second time around they look like that, and then the 3rd time they sort of connect. So I guess we could call these, so they don't intersect in a column, we could call these column strict cylindrical, because again we go from sources I1 to sinks I2, sources I2 to sinks I3, etc. And then we end up at sinks that correspond to our first sources. So column strict cylindrical tableau. Now this only works when lambda is a rectangular shape. So k to the r, k r times. The fact that it works for some partitions might make you think that perhaps it works for all partitions. And as far as everybody is tested for small values of k and r, for small values of n, lambda being a partition of n, it looks like this function evaluates non-negatively on totally non-negative matrices. The end.